Okay, what I'm going to do in this lecture is run through some of the questions on the practice exam paper. I'm not going to go through all of them. I'm going to go through some of the questions which have caused perhaps difficulty in previous years. Uh, I should say, quoting Shakespeare, I'm not bound to please thee with my answers. So, what's this about? As I said, it's going to be a brief run through some of the questions in the practice exam paper which was published on Canvas. I'm going to give some suggestions about what not to do. I'm going to give even more suggestions about what to do. That is, aside from the obvious, such as remember to bring an HB pencil, not to bring a calculator, even a soroban, that's a classical Japanese abacus, to go to the correct exam location. This is a problem with split site exams. Everybody converges on the room where I happen to be standing outside. If the exam is split site, go to where you are supposed to go, the one you've been given, not to the location where I happen to be at the time. So go to the correct exam location at the correct time on the correct date. So, one of the first topics we looked at was that of numbers and polynomial properties. Typical question you might see is about properties of a given polynomial. So one of the questions is, which of the following statements about the polynomial x raised to the power 4 plus 2 multiplied by x squared plus 2 is true? That it has no rational roots, that its only integer root is minus 1, that at least one of its roots is rational, that all of its roots are integers, or that all of its roots are rational numbers. So we're faced with a question like that. One of the things one should do in tackling it is to look at the polynomial description that's given. And one thing one notices about that degree 4 polynomial is its roots have similar properties to this quadratic, y squared plus 2y plus 2. All we are doing is taking x squared and substituting y for it. And that we can analyze just as a standard quadratic. So what we find, returning to the question, it is no rational root. And that statement is true because in fact that polynomial y squared plus 2y plus 2 has no real roots. So it doesn't have an integer root x equals minus 1, doesn't have a rational root. What about vector spaces? So again, typical sort of question we might see, given a collection of 3 vectors defined over the integers working modulo 16, And the condition on these three vectors is that when we multiply the three components together, we get an even value. That's all that mod 2 means. And we might ask, which of the following statements is true of that collection of three vectors? Is it a vector space with that basis? Is it not a vector space because it fails to be closed under scalar multiplication? Or is it not a vector space because it fails to be closed under addition? Is this particular vector a member satisfying that property? Or is that particular vector 2a3 not a member of the collection? If we're tackling a question like that, important thing to be sure of is that you know exactly what a set being closed under some operation means. What it means if we take an operation, say like addition, we take any two vectors in the set, we add them, and we get as a result a vector in the set. Similarly with scalar multiplication. We take any of the underlying scalar constants from which the set is defined. We multiply any vector in the set by that constant, and the result is still a vector in that set. So make sure you know what closure means. Make sure you know what the concept basis of a vector space means. You should also, because typically questions are going to use the operations of modular arithmetic, make sure you're comfortable with working with modular arithmetic. If we're dealing with arithmetic modulo k, you are only dealing with the integers not 1, 2, 3 up to k minus 1. So x plus y in this system modulo k, that is the remainder after dividing the number by k. So turning back to the question, that collection is not a vector space with that given basis. It is closed under scalar product because the only two numbers we have to consider are 0 through to 15. Now, if a vector is in that set, then it satisfies the condition that multiplying all three components is going to give an even value, something which is equal to 0 mod 2. Now that's not going to change if we multiply that vector by any of the digits 0, 1, 2, 3, all the way up to 15. It is also the case that that collection is not closed under addition. How do we see that? Well, the vector 0, 1, 1 and the vector 1, 0, 0 are in this collection U. Multiply 0 by 1, we get 0. Multiply 1 by 0, we get 0. When we add those two vectors, however, we get the vector 1, 1, 1. And 1 multiplied by 1 multiplied by 1 is equal to 1, an odd number. So that collection is not closed under vector addition. That's a true statement. The component, the vector 15, 15, 15, that is not a member of that set. 15 is an odd number. When we cube an odd number, we're left with an odd number. On the other hand, the vector 2, 8, 3 is in that set. 2 is an even number. When we multiply 2 by 8, we get 16. Multiply 16 by 3, we get 48, an even number. After we looked at vectors and matrices, we moved on to calculus. A typical sort of question that we see with calculus concerns critical points of functions. So you might see a question such as you're given some function, let's say e to the power x divided by x, and you're asked again which of the following statements is true. It has a single critical point, which is a minimum, a single critical point, which is a maximum, no critical points at all, multiple critical points, but they can't, sorry, critical points which cannot be classified, or it has multiple critical points. So we're dealing with that question. First thing we have to do is find the first derivative of the function. Now in this case, fairly basic function, and we find its first derivative to be e to the power x divided by x multiplied by 1 minus 1 over x. One thing I should stress is when you see questions involving differentiation on the paper, they are all going to be fairly straightforward functions, I think. So there'll be polynomials, there'll be simple expressions involving logarithms or the exponential function. So if we look at that function and we then ask, is it possible for the first derivative function, e to the x divided by x multiplied by 1 minus 1 over x, is it possible to choose a value of x which makes that 0? And we cannot make e to the power x divided by x equal to 0 because the exponential function is always positive. But if we choose a value x equals 1, then 1 minus 1 over x becomes 0. So that function does have a critical point. In fact, it has exactly one critical point. If it didn't, then the answer, if it had no critical points, the answer would be C. If it had at least two critical points, the answer would be E. But in fact, it has exactly one critical point, x equals 1. In order to classify that critical point, you have to apply the second derivative test. In other words, you take the first derivative function at palm of x, you differentiate it again, and then you evaluate the second derivative at the critical point, the point x equals 1. Whether the outcome is negative or 0 or positive determines whether it is a maximum, unclassifiable, or a minimum. Looked at optimization, which is one of the main reasons why we are interested in calculus from a computer science perspective. So a typical sort of question you might see, you're given a function arising in some application context. Here it's the throughput of a shared printer when some number of users are accessing it. And you want to find out what is the number of users should you be allowed to use things simultaneously in order to maximize the throughput. If the utility isn't maximized, then the printer isn't being used to its full capacity. So, how do we do this? Again, similar to the last question. The first step, find the first derivative. And if we look at that, we see, well, we have 75x squared, the first derivative of that function, 150x, and we are subtracting from that the first derivative of 10x cubed, which is 30x squared. We then have to find the critical points of that function, and we discover that the critical points are when x equals 0 and x equals 5 are two critical points. And then we can use the second derivative test to uncover which of those two maximizes the outcome. What about, we also looked at the concept of optimization where we have more than one variable. So again, typical example, you will see you have some two variable function and you are asked to find what are the values of those two variables that will minimize or sometimes will maximize it. And again, very similar approach. Find the partial derivatives of the function with respect to each of the variables. In this case, we find the partial derivative with respect to x, 2x minus y minus 4, the partial derivative with respect to y, 2y minus x minus 10. We then have to solve simultaneous equations. We have to identify values of x and y that make those expressions equal to 0 at the same time. And what we discover is a value x equals 6 and y equals 8 have that property. Moving on to complex numbers, we had a fair amount of material on complex numbers. I'm going to concentrate on two particular aspects. So one of the questions you might see concerns simplification of complex number expressions. So you might see something like you're given the complex number, say 4 minus 3i, and you're asked to describe what the complex number 8 minus 6i divided by that is in its simplest form. Now, in some examples, you will actually have to work out what 1 divided by the complex number is. And that is complex conjugate divided by its size squared. So in this case, the size of 4 minus 3i is the square root of 4 squared plus 3 squared, the square root of 25, which is 5. The complex conjugate, that's given by flipping the sign of the imaginary part. So the complex conjugate of 4 minus 3i is 4 plus 3i. In this particular case, we don't have to worry about any of that, because if we look at 8 minus 6i, that's exactly the same as 2 multiplied by 4 minus 3i. So we're being asked to simplify the expression 2 multiplied by 4 minus 3i divided by 4 minus 3i. And of course, that's just equal to 2. One of the topics that arises, particularly with respect to the Fourier transform, which you will not be asked any detailed questions about, concerns this notion of a primitive root of unity. So, question you might see in some form are to identify the primitive, let's say, sixth roots of unity with respect to arithmetic being carried out modulo 10. In other words, with respect to arithmetic, where you only look at the last digit, the least significant digit of the number. So how do you deal with this? First of all, you only have 10 possible choices. 10 different digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. For each one of those, you have to consider the result of raising that number to the power 6, subtracting 1 from it, and if the result is equal to 0 modulo 10, in other words, its least significant digit is a 0, then that case is a primitive sixth root of unity. Now we go through that set. What we find is there are only two primitive roots, the numbers 1 and the numbers 9. 1 raised to the power 6 is 1. 9 raised to the power 6 is 81 cubed. 81 ends in a 1. Any number that ends in a 1 when we cube it, or square it, or raise it to any power whatsoever, is going to end in a 1. In general, if you are asked a similar question, but this time for a kth root of unity, with arithmetic being carried out modulo some value m, the only digits, the only numbers you have to consider in answering that are the numbers 0, 1, 2, 3, all the way up to m minus 2, m minus 1. And what you have to do, you take each one of those, you raise it to the power k, you're being asked for a kth root, you subtract 1 from the result, and if it is the case that the resulting number is an exact whole number multiple of m, then that value is a primitive kth root of unity using arithmetic modulo m. Moved on to spectral analysis. I should point out you are not going to see any involved questions concerning complex statistical functions or concerning linear regression or applying linear regression. So I'm going to move on to spectral analysis, which concerns these objects called eigenvalues and eigenvectors of matrices. And sort of question you might see, you're given an example matrix, you're given an eigenvalue of that matrix, and a collection of vectors, and you're asked to identify which of the collections of vectors is an eigenvector for that matrix with respect to the eigenvalue. So, suppose those are the vectors you're given. How do you go about this? You take the matrix, you take each vector, and you compute the result of multiplying the matrix by that vector. Now, if the outcome is some real value r multiplied by, is some whole number value r multiplied by the eigenvalue lambda multiplied by the vector, then that is the eigenvector that you want. Now, it is not always, in fact, it will in general not be the case that r is equal to 1. So it won't be the case that multiplying the matrix by one of the given vectors gives you lambda multiplied by the vector again. There will be some scalar multiple of it is the outcome. One of the other applications of spectral theory concerns its use in algorithmic graph theory. So we have one of the classical applications concerns graph coloring. So you have a 10-node undirected graph, and if we look at the adjacency matrix, we have discovered it has the largest and dominant eigenvalue of 6, and a smallest eigenvalue of -3. And from that information, you can determine bounds on the minimum and maximum number of colors that are needed to color its nodes. How do we do that? The maximum we need is 1 plus the largest eigenvalue, 1 plus lambda 1. The minimum we need is 1 plus the largest eigenvalue divided by the absolute value of the smallest eigenvalue. So we apply it in this case, 1 plus lambda 1, 1 plus 6 is 7. Minimum we need at most 7 colors, and we need at least 1 plus 6 divided by 3, 1 plus 2, which is 3. At most 7 colors, at least 3. We'll sometimes find a situation where those values are not whole numbers. When we're dealing with maxima, and we have a calculation that results in something which isn't a whole number, we round down. Similarly for minima, if our outcome of the calculation is not a whole number, we round up. And this is because you can't have fractional colors. The final application I looked at was an image compression using singular value decomposition. So a typical sort of question you might see is the following. You're given image dimensions, height 1,000, width 1,000. So that takes up approximately a megabyte. If the image is encoded using 3 matrices U, S, and V, for the singular value decomposition, you may be asked, what are the maximum dimensions of the middle matrix in order to allow a total space under 1/4 of a megabyte? So how do you go about doing that? First of all, you compute how big the uncompressed singular value decomposition form is. So in this case, the height multiplied by the width plus the width squared plus the width multiplied by the height. Now the width and the height in this case are exactly the same. They're 1,000. So this case, the size of the uncompressed form is 3 times 1,000 squared. We want to reduce the size of the middle matrix. And in order to do that and fit within the size constraints we're trying to achieve, we need to find the largest value of k, which has the property of the first matrix, which is size 1,000 by k, plus the middle matrix, which is size k squared, plus the third matrix, which is size k times 1,000. That total is less than 250,000. In other words, it's the largest value of k, for which k multiplied by k plus 2,000 is at most 250,000. You will have, because this is a multiple choice exam, You will not have to compute that directly. You will have five options. Exactly one of those options will be the maximum possible with that property. Some will be too large, some will be too small. Now, in this particular case, we find that k is 118. 118 times 2,118 is less than a quarter of a million, but if we go one larger, we get something which is larger than a quarter of a million. So I hope that gives some kind of idea about typical sorts of questions you're going to see and sorts of areas you should focus on in preparing for them. My best wishes for the exam itself. Thank you for listening.